Okay, motion in 2 dimensions. Let's get started. Basically now what we're going to do is we're going to apply the stuff that we've learned to situational problems. The big focus is projectiles. So like if you, and hopefully we have the maturity to do this, but we'll get some Nerf guns and we'll shoot the Nerf guns. And we'll watch the projectile travel and we'll do some physics on that. Yeah, if we're mature enough, we can do that. Yep. So for example, if you look at the picture, you have like a ball being thrown up in the air. So if you give the ball an initial velocity, look what the diagram is representing. You can take that initial velocity vector and break it into its components. So if I do that, okay, it would be different than if I did this. What changed on those two?
That went a little more further.
Lots of stuff changed, right? The x distance, the y distance, the angle that I threw it. Like if I just throw this towards me like this, was there much of an angle on that one? And then if I throw this one to Morley like this one, there was lots of angle, right? So that's the kind of stuff we're going to look at. There's a good throw. You guys don't even know what a good throw looks like. So yeah, hopefully that's a bit of a good introduction. Where did I put my pen? Okay, here we go. Oh, they changed some stuff on here. Cool. Okay, so we're not going to do this because we've done this a lot. Is this in your notes? Pre-quiz example? Okay. You guys can do this one on your own if you want. All you have to do is put the y components together. So you would get a y total for this. And then you would put the x components together, get an x total. Be careful about sign, and then you would do the same business that I did here. So I will leave this one as exercise for you guys. Okay? You guys can do this one on your own. Okay, let's try this one together. So this is just going to be a very basic example of breaking down the velocity vector into its components. So to fly from Vancouver to Edmonton, a plane travels at 49 degrees north of east at 450 kilometers. Draw the vector. So obviously, in real life, the plane not only has to take a two-dimensional vector, but also there's three-dimensional vectors in play too. You got to find it, the altitude, and then as well, right? So, but in physics 20, all we ever care about is the two-dimensional vector. So 49 degrees north of east. How do you guys start these vector constructions? Like, to be honest, I would just, that's really fat, but I would do it really thin. What you can do is draw a really thin grid like that. Maybe if I zoom out. Nope. Anyways, draw a really thin grid like that. And then it's easy to sketch out the vector, like 49 degrees north of east. So you know you're going to be in quadrant 1. So like I might even just draw a horizontal one. And then like 49 degrees, you can roughly estimate that. It's like just past like half of 90. So, and then I just need to draw in an arrow like this. The hypotenuse is the magnitude of the vector. You put 450 there. If you're lazy, you omit the unit. If you're not lazy, you put the unit in. And we have the 49 degrees just rising from the horizon like that. If you like different colors, this would be a good time to do that. You have an x component of this vector. It's east pointing this x component. The other component drawn tail to tip is a north pointing vector. So you have x and you have y. Those components form the right angle triangle. And you should always draw them tail to tip like that. When you have the hypotenuse, like when the hypotenuse is known, I want you to just think about these equations like opposite over hypotenuse. If this one is known, the hypotenuse is known, you can always just slide it up to the top, right? Hypotenuse sine theta gives you the op, and hypotenuse cos theta gives you the adj. So these are like some shortcuts that probably you guys are very familiar with. And in this case, because the angle was made with the x-axis, there's a reference angle with the x-axis, then the op is the y, and the adjacent is the x. If the angle is made with the y-axis, that changes. Is that clear? Okay, if you're, like, if we were using 49, what's the complement of 49? 41. So if you used, and you don't have to draw this in. It'll make your diagram a bit messy. You can if you want, but if you were going to use the 41, the angle made with the y-axis, you don't have to draw this. You can if you want, but here, now the y value, the y coordinate would be the adjacent to 41, and the x value would be the, that should be straight. The x should be horizontal, and the x is now your op, if you make it with the y-axis. But so I always prefer, myself personally, the 49-degree version when it's made with the x-axis. I prefer that. I'm used to y being the sine and x being the cos. It doesn't have to be like that, but that's my preference. Okay, let's just actually solve the problem now. What you can do always, as just like a good first step, is to just find those components. Y will equal 450 sine 49, and x will equal 450 cos 49. So a strong math science student will understand the difference between the x and y, the op, the adj, the sine, the cos. That is pretty natural for a strong math science student. You can get those values. Again, if you have an old calculator, you need to be writing at least 3 decimal places. If you have the new calculator, you can copy paste. 450 sine 49. 450 cos 49. 295. Okay. I'm lazy with the components because the picture sort of implies what's going on. The y is positive, the x is positive, so just by looking at my picture, I can make those assumptions. Some of you might want to write down the units and the direction on those components just to be sure. Anyways, we can continue on. The question says, how far east would the plane travel in 2 hours? The plane isn't just traveling east, it's also traveling north, right? But the question is specifically saying, how far east? So what it's asking is, what is the displacement in x? That's what it's asking. So if you're trying to find the displacement in x, you have to be dimensionally consistent. You understand that this is a uniform motion problem. It's not accelerating. It's giving you a constant speed, so d equals vt. with the added subscripts of x. It's just d equals vt, uniform motion, d equals vt, but with the subscript x to just remind you that you're finding the horizontal displacement. So then I would have to use 295.2 meters per second multiplied by 2 hours. Oh, sorry, that's in kilometers per hour, my bad. 295.2 kilometers per hour for 2 hours. 590.4. So the 590.4, we got to go like significant digits here. 5.9 times 10 to the 2. And that's kilometers. So, like the answer, the numerical value, like sure that's nice, but it's the process of understanding the component analysis. If they're asking just how far east it's going to go, I want to use the horizontal component of the velocity. So again, just so everyone's aware, this is the velocity. This is the velocity. 450 is the velocity. That's what's happening. You could imagine mathematically that this is Vx and this is Vy. Those components are meters per second east and not meters per second. Why do they give stuff in km per hour? Km per hour east and km per hour north. I hope that's clear. Okay, so you guys can try the next one. How far north would the plane travel in 2 hours? So how far north? Make sure you highlight that word north. And hopefully you adopt these subscripts because it will help you stay organized, especially when you got lots going on in a problem. So now I'll use the 339. Do you guys agree? And by 2 hours, hours cancels, you get 680 or something. So 6.8, very nice, Maria. 6.8 times 10 to the 2 km. Yep. Sort of implied because it's asking how far east and how far north. But yeah, you can definitely put that in. Now this is just a qualitative question. These previous questions were quantitative. You're trying to like determine the value. This last question is qualitative. If the wind pushes the plane's velocity vector south, how would that affect your previous answers? So imagine you're trying to run into the wind at an angle. Imagine running into the wind at an angle. I'm running like this, but the wind is coming like that. I'm running at an angle, but the wind is coming at me head on. What's going to be affected? All components? One of the components? Because the wind is only pushing south. Good. So, displacement in x would be unaffected, which for some people seems really odd. You would still displace the same horizontally. You would. But dy would be affected, and therefore the result would be affected. I'm not sure if you use effect or affect. Pretty sure it's effect in science and affect in English. I have no idea. Okay. Tailwinds, headwinds, and side winds. That's basically what we're talking about. So just imagine the plane's velocity is 100 kilometers an hour south. And the wind's velocity is also 25 kilometers an hour south. So the resultant velocity would be 125 kilometers an hour. Okay. How many of you guys ride the train? The LRT? Okay, so just watch me. You're sitting on the LRT. It's not moving. It starts to move. You go like this, right? Okay, that's a little bit of acceleration and some Newton's laws we'll cover in the next unit. But eventually this train just starts going at a constant speed and then it's pretty normal for you in there, right? That's called, yeah, it's like it's not even moving. Very good observation. That's relativity and that's called an inertial frame. And pretty much whatever's happening in that inertial frame would be no different than like being in this room. It looks like we're not moving, right? Although the Earth is flying around the galaxy, right? But does it feel like we're moving? We're accelerating? No. This is a little bit of relativity. So when you're on that train, and it's say that train's moving like 20 kilometers an hour, and then you get up and start walking 5 kilometers an hour in the same direction as the train, what are you moving? Yeah, they add on to each other. To an outside observer, though. To the inside observer, you're going 5. Okay? So Warsami's outside the train. The train is moving this way at 20. I start moving at 5. Warsami sees me going 25. Gervie's on the train. He sees me going 5 because that's what he thinks is reality. But outside of our reality, Warsami thinks we're going 25. Okay, so that's called relativity. So in this case, you can just think of these velocity vectors compounding. And if you guys have done any reading on your own, like Einstein and special relativity and general relativity, there's some pretty interesting things that come about, like with light. So like if you're traveling at the speed of light, and then you like turn on your high beams, like it's all like a mind experiment. You're going the speed of light in a rocket ship, and then you turn on your high beams, your headlights, and those are now going the speed of light. So are they going twice the speed of light? Yeah. So, yeah, in his special relativity, he said that nothing goes faster than the speed of light. So then to adjust that, then you get like the slowing of time. Exactly. That's the question that he proposed. And then his result, and what made him such a genius, was he said that nothing could go faster than the speed of light. And then to adjust for that, you have to affect time and length. It's called length contraction and time dilation. So like when you're going the speed of light, time actually stops. So it's all really cool stuff, but in physics 20 it's kind of like just the bare bones. So plane velocity, if you're going 100 kilometers south and your wind velocity is 25 kilometers north, they work against each other, right? So now as a result, it's like a net velocity of 75 south. Just imagine running into the wind or running with the wind, right? But what about if the velocities are not in the same direction? Those ones were both dimensionally consistent. They were both north and south. But these ones are perpendicular to each other. You have a south and a west. The south and the west will combine as a resultant, like you've been doing in the previous class. You have to add these guys tail to tip, do a little Pythagoras. Is that clear? So that's the kind of stuff you'll see in this class. So I have to pause the video to show you this. Okay, so this should work, I think. There it is. So these are going to be called the riverboat problems, and you're going to have the riverboat problem on your exam. No surprises. And I've mentioned it before, but basically you have this boat trying to travel across from one beach to the other beach. And you notice in the bottom diagram it's totally unaffected by the current because there is no current. But in the top problem, it's like, which way is it pointing in the top box? It's pointing exactly west. It's trying to go west. You're in the boat, you think you're going west, but there's this river pushing you north, and you end up, pardon me, east. You end up displaced. See how much you're displaced? You wouldn't even notice that if you were driving and like the current was like subtle. You wouldn't even notice that. You have some vertical displacement. That vertical displacement is completely dependent on what? And we can't talk about forces yet. We haven't talked about forces. You can only talk about speed, distance, and time. What's the vertical displacement affected by? Both time and the speed of the current, right? If the current's going super fast, you might end up more displaced. If it's just a small current, you would have just a tiny displacement. Yep. The boat's original velocity plays a part in it too. Good. All right, let's keep rolling. I'll show you how to solve these problems. All right. As a boat crosses a river that is 100 meters wide, its motor pushes it at 5 meters per second east, and the current pushes it at 3.5 meters per second north. So it's really similar to the picture we were just looking at. It asks us for the resultant velocity and direction, how long it's going to take to cross the river, and then how far downstream the boat will end up. So first things first, we're going to draw a picture. I recommend that you guys draw your picture the same as me every time. It just works out really nicely. So you got like one beach, you can draw that however you like. And you got the other beach, you can draw that however you like. But basically you just need two vertical lines. Okay, draw your boat. It can be a dot, it can be a box. That's pretty much very typical in physics, a dot or a box. And you want to draw in those vectors. The boat crosses the river. Its motor pushes it at 5 meters per second east. So what's the boat's velocity? 5 meters per second east. Velocities are vectors. Vectors can be represented by arrows. Vectors have magnitude and direction. This magnitude is 5.0 meters per second, and the direction is indicated by the arrow. I would call that VB. Why? Velocity of the boat. Excellent. Then you have to consider the current. What's the velocity of the current? 3.5 meters per second north. So you are going to draw that one. Tail to tip. What are we going to call that one? VC. Good. Velocity current. 3.5 meters per second. So my blue arrow should be a little bit smaller than my black arrow. I'm not sure if that's been clearly demonstrated, so I will do it a little bit differently. Why is that the case, you guys? Yeah, 3.5's magnitude is smaller than 5. Excellent. And the arrow's size gives some indication of the magnitude. Now, What's actually going to happen is the resultant, which for some reason I've decided to color in red. So that one I just call R. Resultant. The resultant is very easy to calculate. X a square plus a y a square, and the theta would be the y over the x. So my diagram is sucky. I'm going to put this 5. I know, right? Alright, let's just clean this up a bit. The vertical was 3.5, the horizontal was 5. Plug those into Pythagoras, you get 6.1. Okay, beautiful. And the direction? Obviously it's going to be north of east, but what angle? Okay, 35, I agree. Anybody have any issues with that? At this point, that should be pretty clear. You guys feel okay about that? That's going to be like on a written response question for like a riverboat problem, that's going to be 2 out of the 5. So if that's all you can do, you get 40% on the question. If you can't solve any of the rest of the part of the problem, then you don't pass the question, and you likely don't pass the exam. So what we have to actually be able to do is all this stuff underneath. So we've done the first bullet. Do you agree? Done the first bullet, right? Okay, second bullet. How long will it take to cross the river? Which vector is crossing the river? The 5, right? And the 3.5 will just sort of push you vertically. You are still going to cross the river. Let's just say that the vertical component doesn't affect the horizontal component in terms of the time. Okay, so the Vy doesn't. Now I'm going to use an E just to really mess with you guys. The Vy doesn't affect the time taken to cross. And for some people, that's kind of hard to accept at first. I probably have to demonstrate it in a lab to really prove this point. We just don't really have the equipment. I might have to like set up a fan, get a fan blowing, and then like roll a ball. So like if there was no vertical current, you would still get the cross in the same time as if there is a vertical current. Is that clear? Yep. Because horizontally, you're still covering the same amount of distance in the same amount of time. So horizontally, you have so many meters to traverse, and your Vx remains constant the whole time. So you will travel a certain amount of horizontal distance in a certain amount of time, and it's unaffected by the Vy. So how long will it take to cross the river? What are we trying to solve for? Time. Is this uniform motion or non-uniform motion? Uniform. If it's uniform, that's the one and only time you get to use d equals vt. Uniform motion, d equals vt. Why am I using the x components? Because what's the distance I've been given? And that 100 meters is what? Good. That 100 meters wide, that is dx. It's not dy. It's the distance across. And if you take a look at the way I've drawn my picture, this is dx. So you could add that into your picture. dx is 100 meters. So if I had a highlighter, and this is the last question we're doing, so I'm going slow, but that's on purpose, and you'll have time to work, so don't panic. That dx, it goes with the vx. Okay? The 100 meters goes with the 5 meters per second. So 100 equals 5t, so t is clearly 20. Just divide by 5. 20 seconds. What if there was no current? How long would it take to get across? 20 seconds. It's the same. Okay? The dy, or pardon me, the vy doesn't affect it. Now look at this one. How far downstream? You will get it asked like that on your test. How far downstream? So, I'll use my pointer. I'm starting here. I think I'm going straight across, right? But I'm actually going to be pushed like this. I'm interested in how far downstream I've been pushed. So when they say how far downstream, they're talking about, what's this dy? How much have you displaced vertically that you would have never displaced if there was no current? So that's all it's asking. How far downstream will it end up? They're asking for dy. What is the displacement vertically? So if you're going to do dy, what does dy depend on? We talked about it earlier. Depends on how fast the current's moving, right? If the current's going really fast, and if you've ever read like old fiction books, like when humans used to ride on horses all the time, they try to cross rivers. If the river's going too fast, what's going to happen? You're going to get pushed downstream. But if the current's just going nice and slow, you can cross that no problem on your horsey. So what does dy depend on? The vy, right? That's the current speed. So v boat is vx and v current is vy. Can I use this 20 seconds for this time? Absolutely. It's the same time. Whatever the time is for x, it's the same time for y. So time is the variable that can traverse both dimensions. You can put time in x, you can put time in y, and it's okay because it's happening simultaneously. So dy is vy times t. Vy was 3.5 north. T was 20. 3.5 times 20 is 70 meters. And you displace north. And that's it, folks. Displacement? Yeah. Yeah. Yeah, you could use the displacement vectors, yeah. You should try it, see if it works out. You would have to know the time though, right? You would need to find out, it's probably the same amount of work, but definitely consistent. You could do that. Okay, I will throw up some homework for you guys. We can come back to this question tomorrow as a review. So in this homework, that's what you're looking for.